Robert Kolasinski from Sandia National Laboratory, and Robert did his undergrad at Rutgers University, and then his master's and PhD at Caltech, and worked together with the Jet Propulsion Laboratory in Los Angeles also. And I looked at magnetic ion propulsion systems, and I happened to get to know him through joint fusion materials efforts, particularly interested in helium ion implantation, helium bubbles, helium ion beam microscopy, and he was kind enough to come out here today to visit us. Now, he is a staff member at Sandia National Laboratory here in Livermore, and also won the Basic Energy Science Early Career Award for his work. And so with that, I'm very glad that you're able to come and speak about the plasma-facing materials. And please go ahead.
All right, well, thank you very much, Pete, for the introduction. So what I'll be describing here today is plasma-facing materials for magnetic fusion, and in particular how surfaces respond to intense plasma exposure, and what effects can be instigated in the material as a result of that. And so I'd like to just start with a brief word about our laboratory in California. I'm sure most of you have heard of Sandia. The main laboratory is in Albuquerque, New Mexico, but we also have a smaller satellite lab across the street from Lawrence Livermore. And just to give you a sense of proportion, the main lab's about 10,000 people, and this lab's about, the California site's about 1,200, so it's significantly smaller, but our main collaboration is with Lawrence Livermore on a variety of topics. But I think one of the things that it's most well known for is this combustion research facility, and in particular, that's part of the Combustion Chemistry and Materials Center, and that houses most of the fundamental material science, chemistry and physics work that goes on at the California site. And even though you may know of Sandia as having these imposing security restrictions when you try to visit it, actually we have an open campus, and the Combustion Research Center, and a lot of this work is in the open area of that campus, so it's relatively easy to get on site to visit. And most of the work that I'm involved with in some way or another pertains to hydrogen materials research. And so that involves what I'll be describing today, which is magnetic fusion energy research, but there's also a lot of work on hydrogen effects on structural materials. So this is work aimed at hydrogen energy infrastructure, so fuel cell electric vehicles, the pipelines that are used to transport hydrogen to fueling stations, for example, will be subjected to varying pressure loading, and as a result, we have a very specialized laboratories. My colleague Joe Bronovich in my department, and they do very specialized testing in high pressure hydrogen environments to see how these materials mechanically respond to different loading conditions. There's a lot of work on hydrogen storage. What's depicted here is a metal organic framework with sodium alunate infiltrated in it, and I mean, we look at a variety of metal hydrides and lightweight storage materials that are used for the transportation industry. And there's actually a relatively large consortium that Sandia is leading, along with Lawrence Livermore and Lawrence Berkeley labs, including the Advanced Light Source, to characterize and understand the physics of how these hydrogen storage materials really work. And then there's also some more applied programs looking at infrastructure for fuel cell electric vehicles, where they've actually tested systems out in the field. This is my colleague in my department, Joe Pratt, and he's demonstrating here a fuel cell system that was actually on a barge out in Hawaii that they were using to power forklifts. It's a situation where you need portable power in a remote location, and so it's an ideal situation for a fuel cell type device. So magnetic fusion at Sandia is, compared to the inertial confinement fusion program. You may know of the National Ignition Facility at Lawrence Livermore. Sandia has a Z-pinch facility also in New Mexico. Those are examples of inertial confinement fusion. The magnetically confined fusion program at Sandia is relatively small. There's only a handful of us there working on it, and almost all of us are involved with the topic of plasma-facing materials. And so that's what I'll be discussing here today. I'm going to start out with just a brief introduction to the plasma-facing materials and some of the problems that are involved with that type of work, and then I'll describe some of the work that we've done with the tritium plasma experiment. That's a device located out at Idaho National Laboratory that enables us to expose materials to high fluxes of tritium plasmas. That's what's depicted here. This is the target of that device over on the right here. And we've used it to test out advanced tungsten materials. Tungsten is considered the material that will be most prominently used as a plasma-facing material for fusion applications. And then I'll talk about some more fundamental science that we've looked at in terms of binding sites of hydrogen on surfaces using low-energy ion beam analysis techniques. So I think it's, this crowd is certainly familiar with the ITER fusion device, but just for anyone who's not familiar, it's going to be one of the largest experiments ever undertaken in terms of international collaboration. I think there's, the U.S. is only a small partner of this right now. It was originally one of the main partners in ITER, but since the latest design was developed in the mid-90s to early 2000s, the U.S. is actually about a 9% contributor to it. But the main goal, and it's rather ambitious for the device, is it has some ambitious physics goals of demonstrating Q greater than 5 for deuterium tritium plasmas, but then also some technology goals, demonstrating the technologies for a practical power reactor. And just to give you a sense of scale here, this is the standard size, 2-meter tall human being in comparison to the rest of the reactor. So it's quite remarkable. One question that's always asked of me is, how close have we gotten to achieving the conditions required for break-even fusion plasmas? And so this plot here will sort of illustrate that. The main figure of merit for fusion plasmas is the triple product, and it's essentially an indicator of the quality of the confinement of the fusion plasma, and then the central, the core temperature of the plasma is sort of the other figure of merit. And as basically what you need to take away from this plot is you go up to the upper right-hand corner of it, you reach the conditions closer to what's required for ignition. And so the important thing, bottom line, is the energy multiplication factor, the fusion power out, is a ratio of the input heating. And the first device that was actually demonstrated to have good performance was developed in the USSR in the early 1970s, and that was the first tokamak designs. But as you can see, this is quite a ways away from what's really required to get good performance from get close to the conditions needed for ignition. But as time has gone on, through the 70s and the 80s and then going on to the 90s, better understanding of the various conditions required to get better plasma confinement were achieved. And then the most recent work in the Joint European Torus and JT60 in Japan, they've actually come very close to this this band here, which would correspond to the Q of about 1 or so. And for DT shots, as close as they've gotten is about 0.65 or so in the Joint European Torus. The equivalent yield from DT shots in the Joint European Torus, this is located in Cullum, in England, has been about 1.05 or so. And JT60U in Japan, one of the main tokamak over there that uses that's actually being upgraded right now to operate with superconducting magnets, has gotten to about 1.2 or so. The other large tokamaks in the world, worldwide right now, ASDEX in Germany, Tor Supra in France, that's been lately reconfigured as a plasma materials testing tokamak named West. But I guess the takeaway from this is that fusion is really a large international effort, and there's quite a bit of interest in it worldwide. The main tokamaks in the U.S. are probably on the scale of this ASDEX device, the D3D in San Diego, and then NSTX, the National Spherical Tokamak Experiment in Princeton, New Jersey, at the Princeton Plasma Physics Lab. But I think, I mean, in terms of understanding the physics and getting better performance out of these devices, I think there's been fairly steady progress over the various decades in terms of the main figure of merit in terms of the fusion product that's obtained, the fusion triple product, I should say. And I mean, what's interesting is if you compare this with Moore's law, it actually exceeds Moore's law. Now, I mean, it's not exactly an apples-to-apples comparison between the two, but I mean, at least in terms of the main figure of merit for both technologies, I mean, the improvement in the fusion triple product has been rather dramatic over the years. And so,
well, you stopped at 2000.
Yeah, this is from a little bit older paper, but yeah, that's true. Yeah. So that's a good point. Yeah, this is taken from a paper from one of the former ITER directors, and it's probably 10 years ago or so. But yeah, it'd be good to update it. But given that, I mean, increasingly the challenges have been recognized that really there's a lot of concern about the materials, and that could definitely be one of the main limiting factors for magnetic fusion. And will the materials survive the intense plasma fluxes that are imposed on them by the fusion plasma? And considerable interest is made in terms for several issues, particularly tritium retention, and then just the degradation, melting, cracking, and bubble formation in the plasma-facing materials as a result of the plasma exposure. And the portion of the device that takes the brunt of this is this diverter region, where the magnetic field lines are diverted into, that receives the highest plasma flux from the device. And so this is an interior look at the D3D tokamak that I'm showing here. And so for ITER, the main plasma-facing materials are going to be tungsten in the diverter region, and then beryllium on the first wall here. And so the parts of the device that are going to receive the highest plasma flux, highest heat loading, are made from the highest temperature, highest melting point temperature material that can be obtained, tungsten. And then the beryllium is mainly lining the outer walls here due to the fact that it's a low Z material, and as a contaminant of the core plasma, it's not going to, it has a much lower impact per sputtered atom than the tungsten would. And so going forward beyond ITER to an actual demonstration reactor, it's thought that advanced tungsten materials or liquid metals may be necessary to handle these intense plasma loading conditions. But I mean, basically the exposure conditions are quite extreme. You have high-flux deuterium, tritium plasmas, you have high-energy fusion products, 1.4 MeV neutrons, and then also the helium ash, and then also impurities that contaminate the core plasma. And just to emphasize the complexity of this interaction, I mean, often it's easy to sort of think of it in sort of this simplistic version where you have incident ions that sputter impurities from the surface, but in fact, it's a rather complex interaction of many different processes. Chemical removal, implantation, reflection, and ionization, charge exchange, and then also within the material you have defect formation, you have saturation of the near surface due to the implanted hydrogen and the helium species. And so taking into account all these different processes is a daunting challenge. And what was found is that really this first 100 nanometers to 1 micron of the surface are really crucial to understanding how tritium is transported through the material, from a tritium inventory perspective, understanding sputtering and impurity transport into the core plasma, and then also fuel recycling. So it's depicted here, and I won't go into all the details here, but I mean, what you're seeing here is basically retained hydrogen and material that's been exposed to plasma for a variety of temperatures. And what they found is that this lower curve here corresponds to combined helium and hydrogen implantation in the surface. So the helium really helps reduce this tritium inventory near the surface. And then also this is depth profiling, an analysis of, this was exposed to deuterium plasmas, and they're basically looking at the amount of deuterium. The deuterium concentration is a function of depth from the surface. And what they find is that for these cases here, toward the bottom and then going up here, correspond to mixed species plasma irradiation. So much of the hydrogen-containing species are trapped right in the near surface when it's exposed to these helium plasmas. So what's becoming clear then is that the structure of the material in the near surface is really critical. And this is a TEM image of rather low resolution TEM image of the near surface region after exposure to a combined helium deuterium plasma, and you can see the small white dots in this image here correspond to small helium bubbles near the surface. So it's thought that there's a network of closely spaced nanometer-sized helium bubbles that's responsible for trapping of deuterium and prevents further, promotes release during the implantation process and prevents deeper diffusion of deuterium into the bulk. And at higher temperatures, you really get some very interesting effects. And what advanced microscopies have provided insight into is this coral-like structure. So this is an image that we've analyzed here with Francis and also Peter in the helium ion microscope. And what you see here is that this is as a result of helium plasmas. This particular sample was exposed to a linear plasma device at UC San Diego. And you get this rather unusual coral-like structure that's formed. And then this is a TEM image of that, a cross-section of this structure, and obtained by my colleague at Oak Ridge, Chad Parrish. And it provides some sense of just what the interior view of this really looks like. I mean, it's sort of an agglomeration of bubbles. The exact mechanism by which this structure is really created is not well understood, and that's a considerable problem if you have this forming on the inside of a tokamak device, because if you have a high, what they call a disruption or a high flux event that results in melting or sputtering of this material, it's a considerable source of contamination for the core plasma as a result. So there's been a lot of effort to really try and understand the initial formation and nucleation of this structure. So, please go ahead. Yeah.
My problem with this compared to the reactor is that oftentimes people end up using a beam that goes in. And the real plasma is Maxwellian, and it has a lot of grazing incidence. And then the bubbles are slow to form. And I just remember Manfred Kaminsky got it wrong years ago. Remember, he was the guy at Argonne, and he blistered the materials because he had a Bragg peak. And I wonder if you might consider that.
Well, they've actually observed this in a practical tokamak, so they've observed it in Alcator CMOD. So, I mean, and it wasn't like they had to, Alcator has moly tiles on the interior, but they put a tungsten row in there, and they actually ran with the mixed species plasma, and they saw this in there. So it's not strictly an artifact of angle of incidence. I appreciate your point that it has been observed in a practical tokamak environment.
Well, I know that Derner and friends have also tilted the thing and tried to get multiple exposure angles on it.
Yeah. Right. Yeah. So, but I appreciate the point. It is something that has been observed in a practical environment. I mean, it does depend, on. Well, actually, this phenomenon doesn't depend so much on surface preparation. The blistering effect can depend on how the material is prepared, but at least for this coral structure, it seems independent of surface preparation and also independent of microstructure as well. So I will show at least here what the initial nucleation of this type of effect looks like. So you can see that there's some energy dependence to this nucleation of the coral structure. These are relatively low energy here with these were obtained in a helicon plasma device, and at different implantation energies, and so they see some of the initial formation of this sort of coral structure, and it seems to be a pretty strong threshold, only a 5 eV difference between the two cases here, where it's almost completely absent, where you see a pretty dramatic onset of this phenomenon. So, you know, there's been some effort to really look at this, and then also, at least in this case here, look at the formation of you know, bubbles and voids in the near surface as a result of helium implantation. This is again some work done by Chad Parrish, and my colleague Dave Donovan did this exposure at Sandia, and you can see what look to be basically voids in the near surface, and you know, essentially structures that have grown as a result of agglomeration of you know, vacancies within the material. And then deuterium plasma exposure, on the other hand, or you know, hydrogen isotope exposure of surfaces, seems to be somewhat different from the helium exposure. So the helium pair formation in tungsten is, you know, a favorable process. So essentially, two helium in a neighboring interstitial sites within a tungsten lattice are, you know, are energetic. It's energetically favorable for them to form a stable pair and then eventually form a tungsten self-interstitial. But that's not the case for deuterium. So what ends up with, or hydrogen isotopes in general, they migrate into the structure until they nucleate a defect at some pre-existing you know, extended defect, maybe a dislocation loop or a grain boundary, and then the growth of that structure depends strongly on the existing microstructure of the material. And so you can see a few different examples of that. These are essentially focused ion beam profiles of the surface, and then we're basically looking at sort of at an angle of what that surface morphology looks like. And you can see this high pressure cavity that had been created as a result of this plasma exposure. And it's, as I'll go into a little bit later in this presentation, it's absent in the case of the ultra fine grained material. So this is tungsten material with a very fine grained microstructure, where we had sort of titanium dispersoids interspersed throughout it to pin the grain boundaries down and prevent larger grain growth.
Question.
Yeah, sure.
For another application, we're interested in tritium uptake into carbon, molten salt reactors.
Okay.
And I'm curious how carbon-based materials would differ in their behavior from the materials you're looking at. I know they've been studied for fusion application also.
Absolutely, yeah. Yeah, so I have a slide on that a little bit later, but it seems like it's completely due to the specific surface area of the material. So it's just, you know, it interacts and chemically reacts with the surface connected porosity of the material. And we found that in plasma exposures of different CFC materials with different specific surface areas, it was a direct correlation with specific surface area of the material. So it seems to be, so it might be relevant to your application as well. So I have a slide on that later. So I could just pause here for a moment just to show you, just to give you a little bit of a feel for what this, what these images are portraying. So, okay, so for some reason this is not, okay. So I'm not sure. Well, okay, so this is, all right, hold on a second, there wasn't the video I wanted here, let's see. Okay, so this is what I wanted to show you. So this is a basically focused ion beam cutting through a material, and what we're basically seeing is sequential SEM images of what it's slicing through. And then on top, you can see that, you know, we're sort of looking at this at an angle. So on top, we're sort of looking at the, you know, the surface morphology change as a result of a high pressure, you know, pressurized gas bubble forming underneath the surface. And the fib is basically cutting through that material. And beneath there, you can sort of see this cavity formation. So it looks to be as a result of dislocation loop punching that these structures have formed, because you see sort of at some point the shape of the cavity underneath resembles what's on the surface. So it looks as though it basically displaced the, you know, core material toward the surface, and you know, as a result of this really high pressure gas that's accumulated inside there. So let's see. Okay, so what I'd like to now describe is some of our work looking at high flux plasma exposure fusion materials. So I mentioned this tritium plasma experiment at Idaho National Lab, and I don't know if any of you have visited INL. It's the lab that has the largest footprint of all the DOE labs in the U.S., and it's probably the most remote. I mean, Los Alamos is pretty remote too, but I mean, this is way out in the middle of nowhere. And there's this little building out there with a stack, and that's our laboratory. This experiment was developed at Sandia and then eventually moved at over to INL. And it creates a high flux plasma column, about 1 amp per centimeter squared ion current to a surface. And it simulates the plasma flux conditions that you'd expect to encounter in the diverter of one of these tokamaks. And it's the highest flux deuterium tritium linear plasma generator worldwide. So it's a unique capability in the sense that it can handle tritium, but because the same radiation protocols used for tritium, you can also work with other materials too, such as neutron activated samples. And so we've had quite a bit of work with neutron damaged materials. There's a program ongoing, collaboration with the Oak Ridge National Lab, where we have samples exposed in the HIFER reactor, and then they're taken out of the rabbit and allowed to cool for a number of years, and then we do plasma exposure in here, and then do analysis of the trapped tritium and deuterium as a result. We can also look at beryllium in this device, and then we have tritium imaging plates, so we can do some depth profiling and looking at surface contamination of materials as a result. This is the attire which you would wear to go and use this experiment. You can sort of see it in the background here in the glove box. This is a picture of me in there. I always think it's someone wearing this kind of attire and giving the thumbs up would suggest that everything. You wonder if this person understands their situation, if they're giving the thumbs up and saying everything's okay when they're decked out in this extreme gear. The main reason for this kind of thing, of course, is there's tritium contamination in there, and you have to take proper precautions as a result. The real reason to use tritium is just the fact that it provides higher sensitivity than deuterium would. So it's extremely detectable. So if you're doing permeation measurements, plasma-driven permeation measurements, that's going to give you about a factor of 100 better sensitivity than deuterium. And then there's also some specialized effects just due to the tritium. I mean, it's a little bit, it's a higher mass than protium or deuterium, so as a result, there's some secondary mass effect that might have to be taken into account. For the case of looking at permeation barriers or permeation rates through materials, I mean, there is a small amount of atomic tritium in the gas that can interact with the surface, unlike deuterium and hydrogen, that can override a barrier to chemisorption on the surface. So permeation in a tritium environment may not be the same as what it is in a deuterium or straight hydrogen environment as a result.
Can I ask a quick question?
Yeah, sure.
Just for scale, what does 1 ampere per centimeter squared for 5 minutes represent in terms of the lifetime of plasma-facing material in an actual demonstration plant?
Oh, okay, yeah, no, it's definitely very small in comparison to that. So the fluxes that we can get in here are about a factor of 10 less than what would be possible to obtain in what would be expected in ITER, for example. And ITER would be, so that we can run for longer time, so we can get higher fluences as a result. I mean, ITER shot would be 400 seconds or so. I mean, we can run this for hours and hours. So in terms of fluence, we can get, so in terms of flux, an ampere per square centimeter, that's 10 to the 19 deuterium or tritium per centimeter squared. In terms of fluence, I mean, we could probably, if we really pushed it, and get to the mid 10 to the 22 per centimeter square range, and for ITER, you'd probably be about 2 orders of magnitude higher than that. So, I mean, there's a way off from what we can do here, but this is not the highest flux.
Okay.
Yeah.
I just wanted to get it.
Yeah, absolutely.
Thank you.
So I mentioned we did a little preliminary work with CFC materials, and we examined retention mechanisms in CFC materials, and we looked at a few different such carbon fiber composites, including these are SEM images of basically 2D weaves, conventional CFCs, and then the one that is actually used in this is a European CFC. It was used in Tor Supra, and something similar had been intended to be used in ITER until they removed carbon from the strike point, decided to just go with one diverter in ITER. And essentially what we found is that the retention in these is basically directly dependent on their surface porosity. So we did BET surface area measurements on all these materials, and we found that really the retention was just as a result of this interconnected porosity within the surface. And so this was actually in terms of one of the reasons they moved away from CFCs as a plasma-facing material for fusion was just because of this. The retention was so high in the carbon-facing, in the carbon materials, they didn't think it would be tolerable. And so
I also heard that the combination of having tungsten over here and carbon over there, they had forgotten about tungsten carbide.
Right.
To lock the tritium in.
Right, yes.
They hit their site limit in 18 hours rather than 18 years or something.
No, and the co-deposition was a huge problem too. That I think was the killer for it too.
One fine day, all the carbon was gone.
Yeah. So this is a illustration of measurements that we had taken looking at retention in tungsten materials as a function of exposure temperature. And you can see that the general behavior here is that it starts out relatively low or at low temperatures, and then at intermediate temperatures around 200 C or so, it increases and reaches a peak and then diminishes thereafter, and is almost, our detection limit here is about mid 10 to the 18 deuterium per meter squared or so just above our detection limit at high temperatures. And so what's responsible for this temperature dependence? Well, at low temperatures, it's thought that this bubble formation and precipitation and trapping are active, but you have slow diffusion, and so there's not deep diffusion of deuterium or tritium into the sample, and as a result, you have relatively low retention at these low temperatures. Then at intermediate temperatures, you have relatively faster diffusion, and precipitation and trapping are still active. So you get the peak in retention here at, say, 200 to 300 degrees C. And then at larger temperatures, diffusion is very fast, but now the traps aren't as active anymore, and so the tritium retention and the tungsten goes down thereafter. So we investigated this with the tritium plasma experiment. We wanted to look at this precipitation effect in more detail. And so we looked at the same material that will be used in ITER, this ITER grade tungsten. And this tungsten material has grains perpendicular to the surface to promote heat transport away from the plasma-facing surface. And so we looked at these samples. Here's an example of 3 different temperatures, and you can see that these are SEM images, different scales, a low resolution on the left and high resolution on the right. You can see the formation of these small bubble networks near the surface as a result. What's interesting is that in this higher temperature case, you see these bubbles on some grains, but not on other grains. And so we did a little bit more detailed investigation of this, did electron backscattering, diffraction of the surface, looking at different grain orientations. And we found that the formation of bubbles very strongly coincided on grains aligned with this 110-111 slip system within the material. And so, here's a very clear example where you have adjacent grains, where you have very clear example where there are bubbles here but none here. And so it seemed like a potential nucleation mechanism here was that the hydrogen would accumulate at some defect, and if the grain structure was aligned with this particular slip system, it could push the material up and away from the surface and nucleate near surface crack or a bubble as a result. And so we did some focused ion beam profiling, and you can see sort of the shape of these sort of defects. There basically looks like a little crack formed near the surface, and then it filled up with high pressure gas, and essentially inflated this near surface region here. And so we tried to develop a model that could describe this in some detail. So we considered the energetics of hydrogen being transported through the surface using a simple 1D diffusion model. We assumed uniform temperature within the sample, and looked at the diffusivity of the, we're basically treating the concentration of the hydrogen within the material, and then the flow within the traps, and then into the bubbles itself. And then we treated the point defects as saturable traps, assuming that the deuterium would not nucleate any of these defects. And then we looked at the flow of the hydrogen through the material and into the bubbles themselves. And so this is sort of an energy diagram of the hydrogen migrating through the material. So the surface site, hydrogen chemisorbed on the surface, is very stable. But then so dissolution of hydrogen into the material is very endothermic. And so there's a strong barrier to even getting it in there. But with plasma exposures, you're sort of overriding that. You're directly injecting it into the material. And it'll migrate around until it encounters a stable site, such as a vacancy. Vacancies in tungsten have been measured to have an energy relative to the migration energy of about 1.4 eV or so. When it encounters a void, that's an extremely stable state. It recombines into molecular hydrogen and stays in there. And it's extremely hard to get out. So much so that you can actually get in excess of gigapascals of hydrogen in these near-surface bubbles. And when you think about that, hydrogen solidifies at about 5 gigapascals. And there have been studies at Brookhaven National Labs where they've done diffraction to study the structure of hydrogen, and they found that it actually forms a molecular solid at 5 gigapascals or so. So basically an H2 at every lattice site, and it forms a sort of hexagonal structure. And so you can actually almost approach the conditions that are required for that within these small bubbles. And it's enough, it's those types of pressures that are required to expand these bubbles by dislocation loop punching, which is thought to be the main mechanism by which they're expanding. And so based on this, we were able to develop a relatively straightforward model for how large these bubbles, the bubble size distribution. So we measured the surface perforations here as a result of these bubbles in AFM, and did a statistical analysis. We found that they basically conform to a log normal distribution, which is about what you'd expect for a material that is a source-dependent growth that requires a source-dependent growth phenomenon. And then the bubble size distribution corresponded reasonably well to this model that we had developed for a thin layer delaminating from the surface and then being pressurized by internal gas. So, the main conclusion from this, though, is we wanted to see if this would be enough to significantly affect the total inventory of tritium within the material, and how much would it affect diffusion into the deeper traps that might be present within the material. And actually, it's a relatively modest effect. Maybe 2 to 28% of the total inventory would be in these high pressure bubbles. And in the ITER grade tungsten case, it was unable to prevent deeper diffusion into the ITER grade tungsten. So, just strictly hydrogen exposure wouldn't necessarily have such a strong effect on what you would expect for the tritium inventory as a result of this exposure. But combined hydrogen-helium exposure can have a much stronger effect. So, the other issue associated with these near-surface structures is that, if you have a transient high heat load on these structures, it could vaporize, they're not very well thermally connected to the surface, and could vaporize them as a result. And so, it's worth considering different materials that might offer better mechanical properties or mechanical resistance to that. And so we looked at some ultra-fine grained tungsten materials, and that's what's shown here. This is a cross-section. These small, darker grains are titanium. It'd be more appropriate to call them titanium dispersoids, but essentially these pin the grains down to prevent larger growth. And so in this case, the grain size is restricted to about 960 nanometers or so. And unfortunately, the response to plasma exposure was unknown, so we took some effort to really understand this a little bit better. The one aspect that we were unsure of is, you're introducing these small grains here, but titanium likes to form a hydride when it's exposed to hydrogen, with the material just disintegrate when it's exposed to a plasma. And so, I guess this image was actually taken post exposure, and then you can see it has held up reasonably well. What we found is that the titanium seemed to scavenge the oxygen from the neighboring tungsten, and it formed titanium oxide, which is relatively immune to hydrogen, and as a result, it didn't have such a remarkable effect as what we were expecting. But this is, again, electron backscatter diffraction map of the tungsten titanium alloy, and then we did XPS to really examine the composition of the oxide, titanium oxide within the material, and examine the preferred texture of the material. And I think what's most notable about it, the real advantage of the ultra-fine grained tungsten is that it would be more immune to neutron irradiation. It had better mechanical properties, resistance to neutron irradiation, than the standard material that would be used in a plasma, a tokamak device. So the tungsten's already quite good from a tritium retention standpoint. So trying to understand as long as the retention behavior is not adversely affected in a bad way, then this material would be still suitable. So we noticed a slight increase in the tritium retention as a result of exposure to the plasma as compared to some standard polycrystalline materials. But overall, it would probably be tolerable, and it's within the range of variability that we see for different tungsten grades. But the advantage of not having significant surface modification and the potential mechanical benefits of not having potential mechanical benefits of reduced or improved resistance to neutron irradiation would be quite a large positive for this. Let's see, so I think I'm running low on time, so I'll just very briefly go over the final part of my talk, which is we have a technique for looking at the atomic behavior of hydrogen on surfaces. And we've used a technique known as ion scattering. And ion scattering is a form of low-energy ion beam analysis that, unlike most other surface analysis techniques, provides direct sensitivity to hydrogen and deuterium. And these are just introductory slides anyway. The main way in which it works is that you have a beam of low-energy ions that can probe the structure and composition of surfaces. And so you look at the scattered ions to obtain information about the substrate atoms, and then you can look at recoiled hydrogen to get information about the structure of the hydrogen that is chemisorbed on the surface. So we have a unique instrument at Sandia that is capable of looking at this in detail. And we noticed that studies on beryllium crystals are quite rare. It's a material that, due to the hazards associated with working with it, there are not a lot of really high-quality single crystal samples available, and so there hasn't been a lot of surface science work that had been done with it. And so what we did is we used two types of ion beam analysis using helium and neon low-energy beams to characterize the substrate structure and then the adsorbed hydrogen structure. And we were able to, get good atomic crystallographic information about the substrate itself, but then also we were able to determine, let's see, the binding site of the hydrogen on the surface. So this signal here is the signal that arises from the hydrogen binding, chemisorb to the surface. And it's really as a result of ion channeling along different open lattice directions on the surface. So depending on if the hydrogen is sitting in hollow sites or bridge sites or on top sites, the beryllium atoms here, these green atoms, and then the red dots are the hydrogen here. If hydrogen is present within the surface channels, you get a different symmetry to your hydrogen data as a result. And so what we find here is that the data is actually consistent with this hollow site binding, and so it provides a direct identification for where the hydrogen is actually binding on the surface. And then we can, using molecular dynamics models, we can actually simulate our scattering data and then get a direct determination of the height of the hydrogen and basically the bond length relative to the neighboring beryllium atoms, and directly identify where it's sitting on the surface. So this is more of a fundamental science study that we've undertaken at the lab. So let me just conclude with this. So what I've described here is we've looked at materials exposed at the tritium plasma experiment at Idaho National Lab. We did some microscopy to really understand this phenomenon of bubble formation, and we tested some advanced tungsten materials, ultra fine grained tungsten materials, and looked at how they respond to this plasma exposure. And then we've done some detailed modeling of the hydrogen bubble growth, and then finally looked at some of these fundamental science studies, looking at the hydrogen adsorption on the surfaces and specific binding sites as a way of validating some of the density functional theory models that are out there. So this concludes my presentation, and I'm glad to answer any questions you might have. Thank you very much.
Any questions? I have a couple of questions.
Well, you heard I'm interested in carbon also.
Yeah.
So would one be able to look at how hydrogen absorbs onto carbon using similar methods as with beryllium?
Yeah, absolutely.
Do you have any suspicion as to what you would find?
Yeah, well, I guess, I don't know. I guess it would depend on the crystal face, and one concern might be whether or not you get some sort of etching or something like that as a result of exposing it to. I mean, if you had to dissociate it to get it onto the surface, it's just atomic hydrogen. You might wonder if it would etch to the crystal. Maybe it's not maybe it's a little more complex of a process, but yeah, I mean, in principle, this technique would be able to look at that.
There's a famous theory from around here called the BO theory, which stands for Beluch-Olander.
Okay.
And what they did was they found that in fusion applications, the carbon would form methane and acetylene. And it was basically a huge chemical reactor. And that was much faster than any other physics that was going on.
Yeah, that's
Just
correct. Yeah.
Just a very layman's question. Does this, seeing all of these things, these surface formations, would make me very pessimistic about several orders of magnitude higher fluxes?
Yeah, right. Yeah, no, absolutely. I mean, the magnitude of the materials problem for fusion, I think, has not received sufficient attention over the years. I mean, most of the funding and focus had really been on the physics program, but I mean, materials is really, I think, could be a deciding factor in whether or not the materials will survive. So I mean, there's now starting to be more emphasis on, I mean, it has to be a two-pronged approach. I mean, understanding the effects of the plasma, but then also looking at what materials could be developed to survive the conditions. And it might be advanced tungsten is a solution, but there's also a lot of interest in liquid metal materials. And I mean, the liquid metals have their own disadvantages. I mean, initially one thinks, well, this sounds great, they'd be immune to neutron damage and all these other things, but you're dealing with a flowing liquid in a highly magnetized environment with huge heat loads. I mean, there's a lot of questions with that also. So it's a daunting challenge for sure.
But now is it felt that the materials are good enough for ITER?
Yeah, so I think the main concerns for ITER right now are probably melting of the tungsten, and it's unclear. There's very stringent alignment requirements on the tiles in terms of how much of a leading edge they can allow for ITER. And I mean, I think the belief is they can get them within the tolerances required, but if you have sputtering, or if the material is shaped in a way that can expose an edge or something like that, can certainly get melting. And that to me, that would be the biggest concern with ITER. I don't know. I mean, I don't know how much confidence there is in that they wouldn't get that kind of melting. They saw melting of the beryllium tiles and the jet tokamak with the ITER-like wall that they've developed. And so that's not as big of a problem, but it's still a concern. So.
Well, there's actually a campaign for ITER to increase the radiation on the outside to decrease the load on the diverter, which sounds sick, but that's what they're.
Yeah, wow. But,
As you correctly pointed out, one of your major problems is to prevent aggregation of either helium or hydrogen. That problem, as you're probably aware, and so I may be bringing coals to Newcastle, is partially solved with the use of these oxide dispersed particles, nanoscale, which you're sort of heading in that direction.
yeah.
It seems to me that thinking about doing the same trick that they've done with helium, which is inert, and therefore the strain field around these nanoparticles plays a large role in how the particles act as a surfactant, essentially, a solid-state surfactant. It seems to me you possibly could do the same thing with hydrogen. You could either form hydrides, or you may be able to aggregate it with, in a way similar as you do with helium, around for example, a titanium oxide nanoparticle. Of course, if you start to form hydrides, you're going to be faced with the problem of making your material structurally unworthy. It's going to become very brittle.
Right.
But maybe that problem can be solved in an engineering way. But I would actually start to think about nanodispersed particles as a way of engineering a material that would mitigate aggregation of both hydrogen and helium. And maybe it would even affect the surface phenomena that you're seeing, since you don't really know what the mechanism is for some of these surface phenomena. They may be emanating from the subsurface region in some way, rather than a simple surface scattering or something like that. So looking at the engineered nanodispersed particles is something that you might start thinking about.
Yeah, I think that's a great point. I mean, admittedly, the materials development effort for fusion in the U.S. has been, I think, way below what it needs to be to satisfy the requirements for ITER. But I think that's an outstanding
It's just an
point.
off-the-cuff idea.
Yeah. I mean, certainly any new concept that can help with that would be extremely important to pursue.
Well, Steve Zinkel from Oak Ridge gave a colloquium here a year ago, and he was talking about composites, tungsten prime
Right.
composites, and also looking at rhenium, if you really want to blow the budget.
Right. Yeah. I mean, at IPP Garching, at the Max Planck Institute, I know they've been looking at tungsten fiber composites, even, where they've used, and things like that. I mean, so they've actually, there has been some work on, what I've shown here is the tungsten titanium, and that's had sort of the most interest recently, but there's been tungsten tantalum and other alloys also.
Yeah, mostly for radiation damage. They
Yeah.
really want to get 100 EPA, and they know how to give you 10. That's
Right.
the disconnect.
the materials development, I think, is something that really needs more emphasis for sure.
Then, thank you very much.